Today we shall learn how to design flange beams, how to design flanged beams. So, our next lecture, design of flanged beams, and again we are considering flexure. This is one cross section of a T beam. We have web and flange. This is BW is the width of the web, DF generally it is depth of the slab, DF generally depth of the slab, and BF is the width of the flange. Here again we consider, we take effective depth D up to the depth of the that level of the tensile steel, and capital D is the overall depth. So, we have two more parameters DF and BF. We have one more cross section that is called L beam. L beam you will find L beam near the edge of the building, because other side you do not have slab. So, you are getting only one side, you are having the flange. So, BW, DF, BF, D and capital D, these are the parameters how you can describe the beam. Let us see that what our code says, IS 456-2000, what our code says, and you will find out in this clause 23.1.1, a slab which is assumed to act as compression flange of T beam or L beam shall satisfy number 1. I have told, please note, I have told that compression flange, because the flange will not be tensile, because concrete will not take the tension. So, always it will be compression flange. The slab shall be cast integrally with the web or the web, and the slab shall be effectively bonded together in any other manner. Either it is cast at the same time, or web and slab, that means beam and slab, that one integrated, maybe due to reinforcement or some other means you are doing that one, that you will get the same that your say deformation, you will get it for web and slab. If the main reinforcement of the slab is parallel to the beam, if the main reinforcement of the slab is parallel to the beam, transverse reinforcements shall be provided as in figure 3 of IS 456, I shall show you. Such reinforcements shall not be less than 60% of the main reinforcement at mid span of the slab. What do we mean by main reinforcement? There is one is called main reinforcement and the other one is called transverse reinforcement. In this case, the main reinforcement is towards the along the longitudinal beam. So, in the transverse direction you have to provide the, if this is the slab and you have the, we are looking for the top, say one beam. So, if you look from this side, I shall get a beam, this is slab and a beam like this. The reinforcement we are providing here along this line in the slab. This is that figure 3 in IS 456, and we have the reinforcement. I have done in the other way, anyway it does not matter. So, I shall show you the main reinforcement of the slab along this line. So, our transverse reinforcement we have to provide this way, and that should not be less than 60% of the main reinforcement. In that case also we can take the slab as a part of the flange as a T beam. So, it bends along this line. So, it should resist, the whenever it will bend this beam, the slab, it should resist. So, we shall get some equivalent length of the flange. Typically what happens actually, say a building, we are considering a building, we are taking a building. We have so many compartments, let us say these are the different compartments, these are the beams, we have say columns here, these are the column positions. We do not need the column, just for to complete this figure, let us say these are the different columns, and these are the slabs. When we are talking this beam, what we can do, whenever we are talking this beam, we shall get the cross section in this way. Now, for design purpose, what shall we do? For design purpose, shall we take only this portion? But that is not a good solution, as if that we are taking that this slab, sorry, this beam is cast first and then this slab, but that is not the case. We are casting this beam as well as slab at the same time, and we can take the flange action of the slab also we can take while designing the beam. So, how far shall we go? If we take the beam, a T beam or a L beam here, we have to specify that there is no problem to define this dW, sorry BW, BW width of the web, depth of the slab or flange df. We can specify the overall depth d, but what about this bf? Or for the edge beam, what about this bf? That we shall find out, and which we call it effective width of flange. We call it effective width of flange. So, effective width of flange according to IS 456 for T beams, we shall get Bf equal to L0 by 6 plus Bw, already we have defined, plus 6 df, the depth of the flange. What is this L0? L0 is the effective span. L0 is the effective span, and that we have to find out from different cases according to IS 456, we have to find out that L0. For the time being, let us consider we shall take it say center to center, but between two supports, center line of two supports. It is possible also that between to that point of contraflexure, that means the point that where you are having moment 0, we shall take that point, between those we can take. So, least of that we shall take it the effective span. Effective span we shall find out, and that we shall come when we shall do the design. Right now we are not doing the actual design, we are doing the part of it, but when we shall do it the design, say a slab or beam we shall design, that time we have to take the effective span, we have to calculate, and that time I shall tell in detail what could be the effective span. For the time being, let us take the center to center between two supports for the time being. Okay. Now, what about L beam? For L beams, it is L0 by 12 plus Bw plus 3 df. Okay. Next one we have for isolated beams, the effective flange width shall be obtained as for T beams, we take it this formula you will find out in IS 456, I have taken it from IS 456 only. So, L 0 by L 0 by B plus 4 plus B W, so L 0 by 6 possibly, this is L 0 by 6. Okay. Yeah.
So, where do you use isolated beams?
Isolated beams is a separate beam we shall consider. That means we are having only one beam, say in the slab we are considering one beam, not the different, the way I have given that one frame, it is not a frame structure, just we are considering between say two walls, we can say that we are having one beam, the spread, that we can consider that as isolated beam. And similarly for L beam 0.5 L 0 by 6 plus 4 plus B W. Okay. Now, let us come to 3 different cases. If we take according to the this is one case, case 1 where neutral axis within flange, that means this is your say neutral axis position, this is your say neutral axis position and the whole stress block is within the flange. That could be one case. How many cases according to stress block, how many different cases can happen, can occur. So, this is one particular case, one case when the whole stress block is within the flange, that means the neutral axis is within the flange, that is possible. The next case is possible. So, we shall come to the formulation again, we shall come, just to let me tell you first what is the first case. The second case is possible, the neutral axis below the flange, that is possible below the flange, neutral axis below the flange, but the flange is uniformly stressed. That means, we are taking this portion, flange is uniformly stressed, this portion is that means 0.45 FCK. 0.45 FCK, that is your say flange, and then we can get that uniformly stressed. The third one possible, case 3, when flange is uniformly okay. This one I have given you just only, let me go back, I shall show. So, what are the 2 different cases, just I have made it little bit elaborate. What I have done here, so we have 2 portions, I think I can come here. Okay. What I have done, so I have done here the whole portion and we are taking that means when we are considering the flange is uniformly stressed, in that case I can take this wave one part and the other part I can take that only flange. So, that means the rectangular portion, the wave only and the flange, that I have taken. So, that you can get it, that yes. So, this is your the rectangular part, which is the whatever we have derived so far, and the other part the portion that flange. So, BF minus BW. So, this one we are having BF minus BW, that because already I have taken this one in the wave, and where we are getting this that 0.545 FCK, that you would say rectangular block of the stress block we are taking. The third case is possible, neutral axis below the flange and flange is not uniformly stressed. So, flange is not uniformly stressed, it means that means certain portion here we shall get, I can show you as if it is like this. So, if this is your stress block, so your flange may come somewhere here, So, this portion is coming within the flange, that is why we are telling flange is not uniformly stressed. So, we have three cases. Case number 1, the neutral axis is within the flange. Case 2, the neutral axis in the wave, but the flange is uniformly stressed. That means, the flange is throughout the depth, flange is having stress 0.45 FCK. And third case, flange is not uniformly stressed, that means, the certain parabolic portion also coming in the flange. So, these are the three different cases you have to consider when you will design that flanged beam. So, let us take one by one. Let us do another part. Let us see from the strain point of view. Our strain in concrete permitted 0.0035 and epsilon s depending on different steel, we shall get different strain. For Fe 415 we shall take 0.0038, let us say 0.004. There is one place here where we have strain 0.002, we have strain 0.002, because above this 0.002 we shall get the stress 0.45 FCK. FCK. So, this is the level up beyond which, that above this we shall get 0.45 FCK. Our question is that let us say this is dF. What should be the maximum dF possible, and this length, that is effective depth d. So, we have d and dF is the depth of the flange or depth of the slab. So, our question is that what should be the depth of the slab. We can write down here dF by d, dF by d will be equal to how much, this one 0.0035 minus 0.002 divided by 0.004 plus 0.0035. I am taking this one whole from this triangle. So, this divided by this 0.004 plus 0.0035. So, I can get dF by d equal to equal to 0.2. So, dF by d equal to 0.2. That means, if we can get that xu by d, we can get x by d. X by d is that one related to neutral axis. Neutral axis from the top fiber divided by the effective depth, that we calculate. So, x by d we can calculate either from the moment or from the section, we can get x by d. So, if x by d is less than dF by d, then we can say that it is within the flange. It is also possible x by d greater than dF by d, but we have to check that whether we are getting that one that uniformly stressed or not, whether we are getting uniformly stressed or not. So, we shall solve few problems, but before that let us derive that which formula we should use. So, this dF by d equal to 0.2 is an important parameter to check whether the neutral axis is within the flange or within the wave. So, case 1, neutral axis within the flange. We can write down the same rectangular formula, mu equal to 0.36 FCK x by d 1 minus 0.416 x by d times, what about the width, b d square, here that width will be bf times d square. Why? Because the T beam we are considering here and the stress block say somewhere like this T and C. So, that means somewhere the neutral axis is somewhere here. So, this is your BF, it is nothing but the rectangular, it is nothing but the same rectangular beam, because the remaining bottom portion we do not that concrete will not take part in any tension or anything. So, in other way, if we can make it like this also, that also, that means this is void, this portion void, because we are providing reinforcement here. So, I can remove that concrete from that portion, because we do not need it. So, we need only at the top, because this one only taking part in the your say bending and compression also that concrete. So, I can remove that certain portion, but we do not do it because that for the shuttering cost or other cost will be more, and so whatever you are going to achieve to removing say your concrete, but your shuttering other things it will again it will cost more. So, that is why you, if it is not at all required, we do not go for this type of cases. Now, mu equal to 0.36, the same formula, only thing change that instead of having just b, we are getting that bf. So, from here we can get that x by d, we can get it the same way. If we know the mu, we can find out x by d. When the cross section we can find out from the expression this is the 0.87 FyAST, that is the tensile force, divided by 0.36 FCK times BF, BF is the width of the flange. So, from here also we can find out that x, x we can find out, that means if the only cross section is given, here moment is given. So, from there we can find out x by d, here also we can find out x by d, in other way I have to write down x by d equal to 0.87 Fy AST divided by 0.36 FCK BF times d. Okay. Now, what about case 2? Neutral axis below the flange and df by d less than 0.2. That means flange is uniformly stressed. Draw the figure once more. And BW, this is BW. and we have D. So, mu equal to mu 1 for rectangular portion, which is nothing but Bw times D plus mu2 for slab, that means Bf minus Bw times Df. So, we are removing these two portion. So, we are doing it separately, Bw and D. This is Df. If I take this portion, Bf minus Bw by 2, and similarly the other one also. So, we are taking these two rectangular portions. So, we have to find out the compressive force. The compressive force we shall get it for rectangular portion, we shall get it, and for the other two sides, the flange portion, we shall take it, which is uniformly stressed. So, we can write down mu1 equal to 0.36 FCK Bw times x times D minus 0.416 x. What about mu2? mu2 will be 0.45 FCK times Bf minus Bw, that is the force, times Df, this is the area times the stress 0.45 FCK, Bf minus Bw times Df, that is the force, times lever arm D minus Df by 2, D minus Df by 2. So, D, and we are taking this portion. So, this is your that lever arm. So, mu will equal to mu1 plus mu2. So, this is your case 2. So, case 1, that simple your say rectangular section, case 2, that we have two parts, one uniformly stretched the flange part and the wave, that which is nothing but the rectangular portion. Yes, back slide. Yeah, is it this one? No, I was showing this one only, isn't it? Okay. Okay. The case 3, for case 3 there is only a small difference. What we do, we get the equivalent depth, this Df, Df is the depth of the flange. What we do, this Df will be replaced by certain equivalent depth of the flange. So, case 3, neutral axis below the flange, and Df by D greater than 0.2, and flange is not uniformly stressed. So, what we shall do, we get YF, instead of having DF we get YF, YF will be equal to 0.15 x plus 0.65 DF. So, we get another rectangular portion, we get YF equal to 0.15 x plus 0.65 DF. So, that one will give us that equivalent depth. We assume that that portion again uniformly stressed. So, we can use that again case 2. So, we modify that DF with this YF. Actually, we are providing DF, but for your calculation we shall use this YF equal to 0.15 x, the depth of the neutral axis, plus 0.65 DF, which will give me the YF, and in place of DF we shall use this formula YF, and we shall get the your calculation. Okay. So, let us solve one problem, then it will be clear. Mainly we are doing say analysis of beams so far. So, BF equal to 1000 millimeter, DF 125 millimeter, BW 250 millimeter, capital D 400 millimeter, area of steel let us be specific, area of steel, tensile steel 5 numbers 20 torr, steel Fe 415, concrete M30, clear cover 25 millimeter. We shall not specify 25 millimeter clear cover and other things also, because we have to assume it suitably. If it is not mentioned, you have to assume suitably, and that you have to write that whatever you have assumed. That is the practice in any design. Assuming that tensile steel yields x equal to 0.87 FYAST divided by 0.36 FCK times BF equals 0.87415 times area of steel. Let us calculate area of steel here. So, I can calculate here area of steel equal to 5 into pi by 4 to 20 square, which comes as 1570 square millimeter divided by 0.3630 times 1000 equals 52.48, and which is less than 125 mm, that means DF, the depth of the flange. X we have got it 52.48 millimeter, which is less than 125 millimeter depth of the slab or depth of the flange. So, neutral axis is within the flange. So, I can write down here neutral axis within flange. Okay. So, neutral axis within flange. Number 2, lever arm depth. Z equal to D minus 0.42 x. What about D? D equal to effective depth. Let us write down here effective depth equal to overall depth minus clear cover minus dia by 2. So, 400 minus 25 minus 20 by 2, which comes as 365 millimeter, equal to 365 minus 0.42 times 52.48 equals 342.95 millimeter. Number 3, moment of resistance due to concrete failure mu equal to 0.36 FCK B times x times z. So, force times the lever arm, which equals 0.36 times 30 times, this is, we can be more specific, say let us say BF. So, BF equal to 1000 times 52.48 times 342.95 equals 1.94378 into 10 to the power 8 Newton millimeter equals 194.378 kilonewton meter. Okay. So, moment of resistance we are taking due to concrete failure. Number 4, similarly we can get it here also, moment of resistance due to steel yielding. So, we can get mu equal to 0.87 Fy AST times Z lever arm equal to 0.87 times 415 area of steel 1570 times lever arm 342.95 equals 1.944 into 10 to the power 8 Newton millimeter equals 194.4 kilonewton meter. So, you will not get any difference in the calculation, only difference we are having that width of the flange, and since neutral axis is within the flange. So, we are using the same equation of the rectangular section, and we can get the moment of resistance taking concrete failure or considering steel yielding. So, what about the then your moment of resistance? Almost same, we are getting almost same value. So, let us come to other case, one more problem. I think we have to, we can finish it. Example 2. Again we are doing the analysis only. BF 600 millimeter. Either you have to calculate the width of the flange according to IS 456, the formula which is given, or it is specified. In few cases it may happen that it is specified, but otherwise we have to get it from the using that formula given in IS 456. So, BF equal to 600 millimeter, DF equal to 125 millimeter, BW 250 millimeter, D 450 millimeter, area of steel 425 torr, steel Fe 415, concrete M20. Effective depth D equal to overall depth minus clear cover minus dia by 2 equals 450 minus 25 minus 25 by 2, which comes as 412.5 millimeter. What about dF by D? dF by D equal to 125 divided by 412.5 equals 0.303 greater than 0.2. So, 0.303 greater than 0.2, we have to use YF instead of DF, because it is not uniformly, the flange is not uniformly stressed, the flange is not uniformly stressed. So, we can say number 2, calculate X for first approximation and we can assume X is within flange, though we know it is not, but we can get the X value using the same formula So, 0.36 FCK BF equals 0.87415 area of steel 4 into pi by 4 into 25 square. How much it is coming? Into 1625 into 4. So, I can take it as 1964. So, 1964 square millimeter. Point 36 times 20 times 600. 600 is the width of the flange. 164 millimeter greater than 125 millimeter. So, that means X is we are getting greater than 125 millimeter. Next step we shall take that we shall assume X now. Let us assume certain X, and that means we shall do it iteratively. We shall get iteratively we shall do the calculation. Assume X equal to 180 millimeter, because it is coming 164, and we have why we are doing, I have assumed that X is within the flange, neutral axis is within the flange. On the basis of that I have got some X. Now, since I know 164, So, I am assuming that it may be 180 millimeter. So, assume x equal to 180 millimeter, yf equal to 0.15 x plus 0.65 df, that equivalent depth equal to 108.3 millimeter. Recalculate depth of neutral axis with yf. So, we can write down x times 0.36 FCK BW, the wave portion, plus 0.45 FCK times BF minus BW, the flange portion, times this equivalent depth should be equal to the tensile force developed in steel. We can write down x 0.36 times 20 times 250 plus 0.45 times 20, that M20 grade, 600 minus 250 times 108.3 equals 0.87 times 415 times 1964 area of steel, which comes as 709100 minus 341100, that if you just rearrange it, divided by 1800 equals 204 millimeter. So, we have assumed x equal to 180 millimeter and we are getting that x 204 millimeter. So, let us assume x equal to 200 millimeter. We have to do it once more. So, let us assume x equal to 200 millimeter. Okay. So, let us assume x equal to 200 millimeter. Yf equal to 0.15 x plus 0.65 df equals 0.15 times 200 plus 0.65 times 125 equals 111.3 millimeter. X times 0.36 times 20, the same equation we are using, plus 0.45 times 20 times 600 minus 250 times 11.3 equals 0.87 times 415 times 1964 or 1800 x plus 3150 yf equal to 709100 or x equal to 199.2 millimeters. That means, if we take x equal to 200 millimeter, so we are getting x equal to 199.2 millimeter. So, in this case we can take x equal to 200 millimeter. Okay. We can take x equal to 200 millimeter. So, 5 moment capacity by taking moments about steel MC1 equal to 0.36 FCK BW x d minus 0.42 x equal to 0.36 times 20 times 250 times 200, 412.5 minus 0.42 times 200 equal to 1.183 into 10 to the power 8 Newton millimeter equal to 118.3 kilonewton meter. MC2 equal to, this is due to balance of the slab, remaining part of the slab equals 0.45 FCK times BF minus BW times YF, not DF, YF because it is not uniformly stressed. So, D minus YF by 2, which comes as 0.45 times 20 times 600 minus 250 times 111 times 412.5 minus 11 by 2 equals 1.248 into 10 to the power 8 Newton millimeter equals 124.8 kilonewton meter. So, we can get that MCU equal to MC1 plus MC2. We shall get MC1 plus MC2. Okay. That you check MC1 plus MC2, and we can get also that approximate formula for steel mu equal to 0.87 Fy AST D minus dF by 2. From here we shall get it, but here I have written dF approximate, I am telling approximate formula, and if we put all the values you will get something 2.482 into 10 to the power 8 Newton millimeter equal to 248.2 kilonewton meter. But here I have given dF because I have not calculated anything. On the basis of that steel will yield, on the basis of that I can get, and I can get the approximate 248.2, and which is coming. If you have, it is a good design, we can come closer to the value, because after all we shall get a balanced section. Okay. So, we shall finish this design of flange beam here. Thank you.